messieurs, je vais en effet vous parler de l'homme de l'an 2000. En réalité, ce n'est pas tout à fait l'homme de l'an 2000 dont je vais parler, car l'homme n'aura pas changé d'ici à l'an 2000. Il n'aura même pas changé d'ici à l'an 4000, d'ici à l'an 10 000. L'homme est une espèce très stable. Il n'a pas changé depuis 50 000 ans, depuis 100 000 ans, et il est probable qu'il ne changera plus. Ce n'est donc pas la transformation structurale ou biologique de l'homme qui va nous intéresser, mais surtout la modification de la condition humaine, des mœurs humaines, des mœurs, et en particulier des mœurs reproductrices de l'homme, sous l'influence des progrès de la biologie. Les progrès de la biologie, en effet, peu à peu, tendent à techniciser, si l'on peut dire, à biologiser l'espèce humaine, à transformer cette espèce naturelle, cet homo naturalis, en une espèce d'homme artificiel, d'homo biologicus. Eh bien, l'une des premières certitudes que nous avons d'ici l'an 2000, c'est que l'homme vivra beaucoup plus longtemps.
« 1958 förutspådde den franske vetenskapsmannen Jean Rostand skapelsen av robotmänniskan som skulle ha högre kapacitet, kunna lagas likt en maskin och aldrig bli gammal. I och med upptäckten av den genetiska koden fick vi den ovanliga möjligheten att en vacker dag bli herrar över vår egen biologi. Idag frigör sig biologerna från evolutionens lagar. De manipulerar levande materia, tränger in i celler, ingriper i deras interna programmering, aktiverar, hämmar, korrigerar och modifierar gener. Genetiken är nyckeln till vår förståelse av människans biologi och försöken att avslöja dess hemligheter accelererar. Ett forskarlag vid Massachusetts Institute of Technology, MIT, har upptäckt en gen som förlänger livet för alla levande organismer, från den mest primitiva till den mest komplicerade. Genen som aktiverats på laboratoriet genom att möss fått speciell föda i väldigt små mängder kan mycket väl vara den gen som avgör livslängden.
So this is about 2.5 gram of food. It's about how much each mouse would get every day. They're usually very hungry, and as you can imagine, they would lose weight. And they are lean, they have a low blood glucose, blood insulin, triglyceride, and cholesterol. So these are all very beneficial to their health.
Calorie restriction is a dietary regimen where you reduce the number of calories that the animal eats to roughly 60% of normal, while maintaining the same number of vitamins and minerals. So the animal isn't actually malnourished, it's just getting less calories. And that extends the lifespan of the animal quite dramatically, and also provides resistance to a wide number of different diseases, including some kinds of cancers, diabetes, obesity, and some neurodegenerative diseases.
This is a fascinating finding that we've known about for a long time. In fact, I think it's by far the most robust way to make a mouse or a rat live longer. But what's been lacking all these years is an understanding of how it works. How is it that diet regulates aging and lifespan? And so this hypothesis that maybe SIR2 and its relatives could be the agents that delivered the benefits of a low-calorie diet was, I think, a very exciting prospect. In fact, it took many years, really 8 years, before we settled on the notion that SIRT1 gene was an anti-aging gene. That is to say, if we increased the activity of this gene, the cells lived longer, and if we decreased the activity, they lived shorter. And what's quite striking is that if you knock out the gene altogether, the mice are quite sick. So this is a gene that in mammals, it's important that it be present. But what's interesting is if you raise the amount of expression of this gene, that the mice adopt many characteristics of calorie-restricted mice. So this, to my mind, fortifies the hypothesis that the SIR2 gene, and in particular the mammalian SIRT1 gene, will mediate at least some of the effects of calorie restriction. And so, for example, the mice with superactive SIRT1 are very lean. They have the blood chemistry characteristic of calorie-restricted rodents.
So we're kind of feeling like marriage, like marriage. It's not very common for people to get married as well. You know, so more common for like.
To continue that path, what one would like to do is to develop a menu of drugs to SIR2s, SIRT1 obviously, but maybe to the other mammalian SIR2s, SIRT2 through 7, and to test these drugs first in animals against various diseases, and then to bring them to the marketplace by testing in humans for benefit against particular diseases. So I think this is the research track that I see playing out in this area of aging and aging-related diseases, is to now develop what we know about important genes and their products, like SIRT2s, to develop drugs that will give benefit for diseases of aging.
Information technology is doubling its power every year. Example, when I was at MIT, a computer that took up actually more space than this room, this conference hall that you're in, cost $11 million, was shared by all thousands of us, and it was really the most advanced computer of any university in the United States. This computer in your cell phone today is 1,000 times more powerful. And we see the same thing in biological sciences and technologies. And we're now really at that early stage of understanding biology. Yes, you've collected the genome. We're in the early stage of really understanding it, reverse engineering how the genome works, how the brain works, how these biological processes underlying disease work. But all of the tools are progressing exponentially. We're doubling the power every year of the ability to simulate, model these processes, reprogram them. And so these will be 1 million times more powerful 20 years from now, and that really will be very transformative.
Inspirerad av några visionärers övertygelse, bland annat den amerikanske fysikern Ray Kurzweil, lockas allt fler vetenskapsmän av löftet om en guldålder för biotekniken. Forskningen fortgår i allt snabbare takt när vetenskapsmän över hela världen jagar efter nya ledtrådar och upptäckter. Vi bevittnar uppkomsten av ett revolutionerande område inom medicinen, regenerativ medicin, som en vacker dag kanske kan vrida åldrandets klocka bakåt. För bara några år sedan lyckades biologer extrahera en cell med extraordinära egenskaper från ett mänskligt embryo i tidigt stadium. Den embryonala stamcellen. Embryonala stamceller har den unika förmågan att förnya sig själva och reproducera sig i det oändliga utan att försämras. De är inte bara odödliga, utan de kan också förvandlas till vilken sorts cell i kroppen som helst. Beroende på den information de tar emot kan de bli till muskler, hud, blod, ben, hjärnceller eller hjärtvävnad. De ger ett obegränsat reservlager av nya, fräscha celler som kan reparera och föryngra skadad eller åldrande vävnad. Ett annat laboratorium vid MIT skapar mänsklig vävnad genom att odla stamceller på syntetiska bärarmaterial som sedan bryts ner biologiskt inuti kroppen. Den dag då hela njurar, levrar, hjärtan, ryggmärg och blodkärl kan konstrueras verkar inte vara långt borta.
There's multiple phases in growing a tissue or organ. One phase is growing the cells, is getting the right type of cells, which could be stem cells and convert them into the right cell type, or it could just be isolating the particular type of cells you need, like cartilage cells, bone cells, and so forth. Another area that's also very important is the materials. What's the right materials for the cell to grow on? What's the right way to manufacture that material to give it the right shape and so forth? We then combine the two. We add the cells to the plastic scaffold, the material scaffold, and then grow it in what we call a bioreactor. And in that stage, it needs the right nutrients and so forth. And then we take the tissue that we create in that bioreactor and actually put it into the animal or the patient. Well, we've worked on about over 20 different tissues and organs over the years. We've worked on spinal cord, we've worked on intestine, bone, are doing some very exciting work on trying to tissue engineer new hearts.
So here is an example of some scaffolds that we have made for stem cell differentiation, in particular for bone regeneration. And these scaffolds are biodegradable in nature, which means that they can degrade so that they will be absorbed by the body. And most importantly, the shape can be molded to whatever thing you want them to become. For example, we can make, like an ear shape, we can make a nose shape, we can make a chin shape from the same material. Trying to make a piece of tissue is very similar to trying to build a house. So cells are like the bricks when we're trying to make a piece of tissue. And also the scaffolds provide structural support, initial structural support.
And one technology we have is microfabrication technology at our disposal. And what we're able to do is we're able to use the same technology used for microchips. So this is developing structures on a very, very small scale, the micron scale. And we're able to use those technologies and interface them with biomaterials. And here I have a silicon mold that mimics the right fluids of the blood vessels that are in your body and mine. And so from this mold, we are going to cast polymer and novel biomaterials onto this mold for eventual use as a mimic of blood vessels found in your body. And I have one of those polymers right here. This polymer is actually very flexible, just like some of the tendons and ligaments in your body are flexible. Another important aspect of those biomaterials is that they are biodegradable. And what this means is that we can implant this material within your body, and over time, those materials will degrade and eventually disappear within your body. And here what I've zoomed in upon is a microfluidic network, which simulates an array of a capillary bed that you'd find within your body. And if we look closer, what we see is micron scale channels that, just like your capillaries, span out and perfuse and feed the cells around your organs.
Here we're looking at a specimen of tissue-engineered heart muscle that we've fabricated by combining neonatal rat heart cells with a novel scaffold material. And the structure here that we're seeing, we're terming an accordion-shaped pore structure. This accordion-shaped pore structure was designed to help mimic the mechanical properties and the structure of the actual heart muscle tissue. And we can see that within this pore structure, the pore is about 400 microns in length and about 200 microns at its widest point. The heart muscle cells filling throughout the pore structure and contracting synchronously.
Right now we're starting very small with a little cardiac patch to be put onto an area that might have been damaged by a heart attack, or a vascular graft that might be put on an aorta or another part of the heart. There are other people that are working on tissue-engineered valves, and so you can envision eventually maybe these approaches could be combined into a full organ repair, but that would be further in the future.
The real goal, the eventual goal, is to be able to fabricate tissues and organs for any patient that might need it. For example, if you need a new liver, if you need a new heart, if you need a new lung, you can simply create a construct which can be produced by essentially a factory, and these organs can be pulled off the shelf and implanted in you, and so you can get your new liver, heart, or lung.
Vetenskapen närmar sig allt mer målet att bemästra stamcellernas fulla potential och kunna skapa levande kroppsdelar för att byta ut skadade och vända åldrandet. Lyckas vi med det är vi nära den gamla drömmen att bli vår egen skapare. Aubrey de Grey, en engelsk genetiker vid Cambridge University, har utvecklat en radikal teori om hur människans livslängd ska kunna förlängas. Han är övertygad om att åldrandet är som vilken annan botbar sjukdom som helst och att döden inte är oundviklig. Men han är kontroversiell och en av få forskare som vågar lägga fram en hypotes om odödlighet.
Something that I think is true is that the first person to live to the age of 1000 has very probably already been born. I would say there is an 80% chance of that. I would say that there is a 50% chance that the person who will first reach the age of 1000 is already 40 or 50 years old. We already know that aging can, in principle, be repaired, simply because we know that the human body is a machine. It's a really, really complicated machine, and we don't have the plans the way we have for man-made machines, but it's still a machine, which means that its functional lifespan can be increased indefinitely by sufficiently thorough repair and maintenance. So in other words, there is nothing more to discover to prove that aging can, in principle, be repaired. What we do need to discover is the details of how to implement these various repair and maintenance strategies so that we will actually have the technology.
We understand how a house works because we created that methodology. We understand all the methods underlying a house, so we can repair them. We don't yet have that knowledge, that set of tools with our bodies, but we're getting there very quickly, and we will get there exponentially. And in my mind, actually, I think Aubrey's projections, although they're considered radically optimistic in some quarters, are, I think, a bit conservative, perhaps by design. In my mind, within 15 years, we will reach that escape velocity where each year we're going to be adding more than a year, not just to infant life expectancy, but to your remaining life expectancy. Now, that's not a guarantee of immortality, but that is an escape velocity. So as you go forward in time, the amount of time you have left actually increases rather than decreases, and that will be a very different experience.
I de mest utopiska visionerna kommer människan att hitta vägar för att öka sin kapacitet genom att koppla ihop kroppens biologiska system med den senaste tekniken. Snart blir omprogrammeringen av vår egen biokemi lika enkel som att programmera om en dator. Det oändligt lillas teknologi har redan börjat producera de första prototyperna för användning inom nanomedicinen. Maskiner som är små som molekyler kan arbeta inuti människokroppen och leverera läkemedel till cellerna. För nanobiologerna kommer de här molekylmaskinerna att revolutionera läkekonstens framtid. Snart kommer inte en enda sjukdom att kunna undgå dem.
Mankind has historically built everything from simplicity. We've always built complexity from simplicity. During the agriculture and mechanical ages, we built everything from 6 simple machines: levers, pulleys, screws, and everything that we built a whole period of time in our history has been with these 6 simple machines. During the electronic age, we built everything with 5 simple machines: resistor, a capacitor, an inductor, and the result of this is that it really limited the complexity of the devices that we could build. Nature, on the other hand, has a palette of tens of thousands of simple machines. And what I wanted to do was I want to have access to this incredible palette of material from which to build devices and machines that have the complexity that's comparable to what you find in living systems. So as a result of that, we have embarked on first trying to figure out how in the world do we harness these individual molecules and assemble them to do things that we want to. And what you're looking at here is one of the first devices that we made. This device is 125 microns from head to tail, and it's fully self-assembled, and it walks along using the energy of these cells come from the hearts of rat pups, cardiac stem cells, to propel them. Once we're able to do this, the concept then became, can I take this machinery and start making it into devices, to rods and levers that we could ultimately insert in the body? So working with this type of material is very exciting, but we really wanted to be able to get deeper down into the physiology of living organisms. We wanted to be able to make devices that we could insert at the most fundamental level of living organisms. So our work began with a molecule called ATP synthase. This is the powerhouse of the cell. And what happens is there's a rod that spins around. As this rod spins around, it moves some cylinders that move back and forth. And this flexure causes the molecules of ADP and phosphate to generate ATP. What we did was we took this portion, the engine portion of it, we disassociated it from the membrane portion, the turbine. Took the turbine, we flipped it over, and so now we have an engine with a shaft coming out. And then what we did was we stuck a nanorod on top of the shaft. So as the pistons were moving and the shaft was spinning, the rod, which made it look like a propeller. That is the original nanocopter. So it's really quite quaint now. But when we're doing it, we had to solve a bunch of problems. We had to learn how to take these molecules and disassociate them, how to develop chemistries to make them attach them exactly where we want to, how to put those molecules where we want to. And they had to be in the right orientation. They couldn't be laying down. They had to be exactly where they had to be. Again, it's nanotechnology.
Okay, how much? Well, let's do something like a 1 to 100 ratio.
1 to 100 ratio, okay. Suppose that is 10 microliter.
Oh, no, I mean 1 to 100 milligrams.
Okay.
The concentration is on there, so it's possible to calculate it.
Okay, I will calculate that. Okay, thanks.
Actually, I'm working on a project using a molecule called 529. It's a RNA motor. It's the packing motor that's used in viruses to pack the DNA inside of the capsid of the virus particle. And we're using this now to engineer a device that would pack the DNA inside an artificial device that we built and then inject it into a cell for a mechanism of gene therapy. The viruses have a container on top. And at the bottom of that container is this motor. And this motor really, what it does is it spins around, and as it spins around, it takes the coils of DNA and it shoves it up inside of this container. So it spins around, the DNA goes up and gets packed up inside there very, very tightly. And then what happens is, after the DNA is replicated and is placed inside there, when the DNA is packed so tightly, it's under incredible pressure. And what happens is, when this virus particle gets to a cell it wants to infect, it gets on the cell, and a door opens up, and the DNA just shoots right inside there. Because on this high pressure, it shoots right inside there, and that's how the cell gets infected.
It's just a very strong motor. And it's, in fact, actually one of the strongest motors that people have found in nature. And so you can imagine that a very strong motor might be useful for moving things that are much larger than itself. So we're trying to take it out of its natural architecture and put it into something new.
Working with hybrid systems, living, non-living, unified systems, provides you the opportunity of interfacing devices that you engineer seamlessly with living systems. What I'm looking at is trying to engineer materials and devices so that when I place them inside a person, that they integrate with the life cycle of that person, they integrate with the energy flow, with the physiology of that person, so that they become part of that person. Instead of being this ugly, at least aesthetically, ugly box that you stick on somebody, what you really are doing is you're engineering a component that provides a function that when it's placed inside that person, you can't differentiate where this component begins or ends and where the living person ends. The interface is so seamless, they meld together.
But if we go out to 2010, I think this technology is going to disappear. We're not going to see it. Devices which are already about this size are going to become so small they'll be embedded in our clothing. Images will be written directly to our retina. We'll create full immersion virtual reality environments from our lenses. And we're going, in the decade, the next decade, is really when these biological technologies will come into fruition. We really will have the means of simulating in great detail the biological processes that lead up to the different diseases that kill us. And we're gaining new insights as to how the brain works, giving us more insight into ourselves. And this will help both with the project of achieving engineered negligible senescence on the one hand, but also this other project to expand our horizons by creating more intelligent machines, which are really an extension of ourselves. And literally we're going to, in my mind, put them inside our bodies and brains to literally expand our capabilities.
Neurovetenskapens senaste framsteg har öppnat spännande men ibland oroande möjligheter. Neuroradiologi, magnetisk stimulering och hjärnproteser ger nya möjligheter att utforska och återställa hjärnan. I över ett decennium har neurobiologer vid University of Southern California utvecklat en hjärnprotes, ett syntetiskt minnessubstitut. Man tror att denna apparat inom loppet av så lite som 15 år ska kunna reparera skador orsakade av neurodegenerativa sjukdomar som Parkinson och Alzheimer och slutligen utplåna senilitet. Kan de här nya proteserna vara det sista steget innan man åstadkommer en frisk hjärna i en odödlig kropp?
Imagine that your goal is to understand how the brain creates memories, right? And we have a lot of theories about how the brain constructs memories and how it recalls memories, and they're very cognitive, they're very high level, they're very conceptual. Now, how do you take a conceptual understanding of the brain? And it's not that it's wrong. It's probably quite correct. But how do you take a conceptual understanding of the brain, and how do you reduce that to a microchip? How do you do that? You know, it's not an easy thing to do, to move these concepts into circuits, into mathematical equations. And I think that, and some people think that our attempt to build neural prostheses for things like memory or for cognition, they think we're crazy. And I think the problem is that people keep thinking about cognition, language, memory, and they think of it in terms of these concepts. Well, why not think of it in terms of signal processing? Because in the end, that's what the brain does. That's what neurons do. They receive electrical signals, they change those electrical signals, and then they have an output of more electrical signals. So let's give a neuron all possible inputs, which would be a series of these random intervals. We stimulate the neuron with it, and then we look at the electrical output of the neuron and ask, what is its output to all of these random inputs? And so we generate a very general model, a model that shows us how real nerve cells would respond to any conceivable pattern. You can give me a dot, 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 any pattern you want, give it to me, and I can program a computer, and we can predict what the output of the neuron will be, and it'll be exactly right. In reality, we probably don't need to know much more than that to be able to replace a part of the brain.
Here's a hippocampal slice. It has 3 regions. The signal passes from here to C3 and propagate from C3 to C1. So if we make a cut between those 2 regions, like what we did here, and we send stimulation to dentate, there'll still be activity in dentate region, but you won't see any response in C3 and C1 because it is damaged. And we did this to mimic what happened in patient where C3 region was damaged. And finally, we built this FPGA chip to replace the damaged brain region. So what the chip does is mathematically predict what the stimulation should be to C1 region. So if you only look at the output signal, in this replacement experiment, you won't see any difference between this and what you observed in the intact slice. And in other words, we functionally replace the damaged C3 region with this FPGA chip.
Brain chip doesn't really repair the damaged region. It takes the place of the damaged region. It's a substitute. And that's what we're trying to do. We're creating a substitute. And what we have to accomplish is not only getting the mathematical model correct and the microchip correct, but then we have to be successful in getting the microchip to communicate with the brain. And that's not easy.
Ça, c'est possible que dans l'avenir, on puisse effectivement imaginer que certaines de ces circuits intégrés mis au bon endroit facilitent la réactivation de certaines mémoires qu'on a pu avoir oubliées. Par contre, s'il y a certaines mémoires qui, vraisemblablement, ont complètement été éliminées. Alors, est-ce que chez ces gens-là, on va pouvoir recréer cette information? Je ne sais pas. Je sais pas. Ça, c'est toujours aussi la même chose. Est-ce qu'on pourra, dans le futur, par exemple, il y a eu plein de films qui ont montré ça, faire un transfert de mémoire d'une personne à l'autre. C'est-à-dire que si une personne a un certain nombre de mémoires, est-ce qu'on peut les transmettre directement donc, par un système donc, de circuits intégrés, de communication de cerveau à cerveau, ou de cerveau, circuit intégré de nouveau à un cerveau, recréer des mémoires artificielles. Ah, c'est une question difficile. Une question difficile.
Att reducera mänsklig intelligens till en uppsättning ekvationer verkar i princip omöjligt. Men ändå arbetar en grupp neuroforskare vid Federala tekniska högskolan i Zürich med att skapa en virtuell hjärna. En perfekt kopia av en råtthjärna. Och till det använder de en av de mest kraftfulla superdatorerna i världen. Om 10 år, när projektet är färdigt, ska Blue Brain-programmet kunna simulera och visualisera de elektrokemiska funktionerna i den hjärna den utformats efter. Och det är möjligt att en gnutta intelligens kan uppstå genom interaktionen mellan dessa miljardtals neurala kopplingar. Forskarna hoppas att den här hjärnsimulatorn ska hjälpa dem att förstå hemligheten bakom människans medvetande.
So what you're seeing here is a fly-through of the neocortical column after we've built it. It's about 10,000 cells. We're only seeing about 10% of them. And the important aspect of this is that you can see that 90% of the brain is branches. And this model, the Blue Brain project, allows us to actually understand and explore the function of these branches. And there is no other way to explore all of these branches working together other than putting them together, building the circuit together. In the end, it is this module, this processor, that will allow us to understand human intelligence. So even though we study this at the level of a low mammal, such as a rodent, it's the first step to be able to go up and understand the core circuit properties in the human.
actually have tremendous facilities in the laboratory for recording from individual neurons, injecting dye into the neurons, and using the biology, measurements of the biology to reconstruct the full three-dimensional structure of the neurons, the full electrical behavior of the neurons. So we have a suite of stimuli that we apply to characterize how a neuron responds to input. And then we combine these to build a single model of a neuron. And then we place these neurons within the volume of a neocortical column such that they correspond to the biological observations of where these neurons occur in the different layers of the cortex.
We do in vitro preparations. So that means essentially we take slices of brain which need to be prepared. So essentially you take out the brain and then shock freeze it, you cut the slice of the brain, and then essentially let the slice rest. You mount it on an object carrier and then put this under your microscope. So essentially once you put the slice under your microscope, you mount the electrode with a glass pipette on top, very thin pipette so that you can penetrate the membrane of a cell, and then mount an electrical connection to the inside of the cell.
Je positionne la pointe de la pipette en direction de la cellule. On approche la pipette de la cellule. Donc là, on s'approche de la cellule. On ne la voit pas encore. Et puis, elle touche la surface de la membrane. Nous avons le contact entre la pipette et la membrane. Nous sommes prêts à commencer à enregistrer l'activité de la cellule.
So this gives us a tool in which we can actually replicate experiments that have been performed in the laboratory and compare the results in the model directly with the reality, and then ultimately make predictions and understand in a more deep way, because we can perform experiments that are simply impossible in the real brain circuitry.
In 10 years, you can imagine that a researcher would put on goggles, enter into Blue Brain, he would enter into a virtual laboratory, and in that virtual laboratory, he'll be able to run all kinds of experiments. We will couple the brain with, for example, a virtual reality entity, an avatar, that will have a blue brain on it, sitting on a supercomputer. You can also connect it not only to a virtual avatar, but actually to a robot. So you could have a physical robot that would be interacting with the world through cameras and recorders, and this information would be injected into the brain, and then it would send commands to drive the robot. So if we build it wrong, this robot is just going to crash, fall, not be able to do anything meaningful, not be able to communicate, and not do anything intelligent at all. Whereas if we build it correctly, we should be able to see it learn like a baby, acquire knowledge, and start to move correctly, respond to stimuli, and communicate. If we finally build the human brain correctly, it should speak a language. You should be able to teach it a language, and it may be able to teach many different languages. So, and then as you teach it a language, you'll be able to see where does the language go, how is it embedded, is it distributed, is it very localized. So you'll be able to ask some very important questions about language generation, and then during the process of language, you'd be able to track every little step and understand this tape recorder that just comes flowing out of our mouths when we speak. how are they coming? Where do they originate from? Where is the mind? Where is the beginning? When I say I want, what is it? What drove that sentence? So with this kind of technology, we should be able to dig down to the very origin of thought.
De etiska barriärerna bryts gradvis ned och kommer inte att stå i vägen för vetenskapliga framsteg mycket längre. Men kan den ohämmade strävan att kontrollera vår egen biologi bli en kapplöpning utan slut? Är den perfekta hälsan en illusion? Kanske kommer vi en dag att lyckas modifiera nya gener, nya organ, nya minnen och till slut avvärja döden. Men någonstans på vägen finns förstås en risk att vi genom det förändrar vår grundläggande identitet.
kanalen.
23.05 följer vi Siskas jakt på den perfekta svenska näsan. Den hon föddes med föranledde nämligen väldigt ofta frågan: var kommer du ifrån? Därefter 11:05 blir det dokumentär om fotbolls-VMs ekonomiska betydelse för Sydafrika. Och nu blir det studiebesök.
Strax ska vi se dokumentärfilmen Som en Pascha. Pascha är Europas största bordell och den ligger utanför Köln i Tyskland. Hit kommer varje dag mer än 700 män för att köpa sex av de drygt 150 kvinnor som arbetar här. Filmaren Svante Tidholm har till och från under 3 års tid besökt Pascha för att dokumentera verksamheten där och för att söka svar på frågan varför sex är så viktigt för män.
En av de grejer som jag ganska tidigt förstod var viktigt för hur vi män fungerar är sex. Så att när jag under fotbolls-VM 2006 var nere i Tyskland för att filma så kom jag i kontakt med den här bordellen och fick tillstånd att filma där mot alla odds. Jag förstod inte hur de tänkte i början, men det var så det gick till. Och jag tyckte den här platsen var så fascinerande. Jag kunde inte sluta tänka på den efter första gången jag hade varit där. Så att jag ville helt enkelt åka tillbaka och eftersom jag fick det så blev det många resor under 3 års tid. En bordell är ju, ska man säga, det är en symbol för hur vi försöker lösa ett problem i samhället. Vi har en massa män som har någon slags idé om sex som inte fungerar speciellt bra. Och bordellen är liksom en idé om hur vi kan lösa det här problemet. Det som har slagit mig på bordellen är ju att det återigen, precis som i resten av samhället, i alla relationer så är det kvinnor som ska ta hand om män. Och det är ju så det fungerar här också. Alltså män använder kvinnor för att komma i kontakt med sina egna känslor eller förstå sig själva liksom.
Ja, du är ju med själv i filmen. Man ser ju dig vid några tillfällen. Hur ser du på din egen roll i själva filmen?
Jag är ju liksom ett åtlöje av mig själv i filmen kan man säga. Men jag tyckte det var väldigt viktigt att vara med. Alltså dels i egenskap av svensk man liksom på den här bordellen. En väldigt udda fågel liksom, som feminist som kommer dit och ställer konstiga frågor. Jag tyckte det var viktigt att liksom hämta hem filmen till ett annat perspektiv och så föra ut det som händer i den här extremt annorlunda världen till någonting annat. Liksom. Och jag var ofta handfallen och visste inte vad jag skulle göra i många situationer eftersom det var så konstigt och starkt på något sätt. Jag tror att det finns väldigt mycket förvirring helt enkelt kring sex. Alltså vi lever ju i en tid när sex och sexualitet är någonting väldigt avdramatiserat på sätt och vis. Eftersom vi ser det så mycket i reklam och kultur och media och så vidare. Liksom. Men det är samtidigt något som vi inte pratar om, tycker jag. Alltså vi tar det inte på allvar. Vi tar inte det som händer när unga män liksom introduceras till sexlivet liksom på allvar helt enkelt. Och jag tycker att vi borde prata mer om hur det påverkar våra liv och hur det påverkar våra relationer. Jag tror det är det som är det viktigaste som jag har fått höra av folk som har sett filmen. Att det är en öppning för att kunna prata om sex i relationer.
Yeah, here we have a room that is prepared for men who have some nurse fantasy. Maybe I can show you. You can dress. And when the men say, okay, I would like to enjoy this fantasy, to make love with the nurse, then he can pick up one of the girls and they can come here. The girls dress up for this here and then they can play here the fantasy like in a nurse, like in a hospital, something like that. This chair is normally from this kind of original thing, and you can do here a lot of things. The man can sit here, and the lady can make it for him the French style, or the girl can sit down here, and the man can make for her the sex style. It's just your fantasy, no? So no limit.
What's the Spanish? What's that?
Spanish. Spanish style is when you put your dick between the breast of the woman and the woman massage your dick as long as you come.
Ser ni huset där borta? Det är en 11 våningar hög bordell. Varje dag kommer hit mer än 700 män. Man betalar 5 euro i dörren. Och då får man tillgång till alla 11 våningarna. Man får gå omkring och välja bland kvinnorna här. Första våningen är snabbisvåningen. För bara 30 euro så får man en garanterad orgasm. Fjärde våningen är asiaternas och 7:e transornas. Det jobbar mer än 150 kvinnor här från hela världen. Och de behöver nästan aldrig gå ut, för huset är som ett eget samhälle. Det finns frisör, läkare, manikyr och en personalrestaurang som är öppen dygnet runt. Det här är Europas största bordell.
I mean, prostitution exists already since thousands of years, and it will also exist in thousands of years. And of course, it have a lot of problems with it. But to control this matter is for sure better when you walk with the people together. We are a big place where gentlemen who feel lonely who need a little bit love or who need some fun can come here and enjoy the illusion of a paradise on earth. The paradise, the ladies are the paradise, because most of the men who come here, we wish they go out like a pasha. This means that they are totally satisfied. And the girls who are here try their best to satisfy the customer here that he feel when he go out like a pasha.
På dagarna så är det mest affärsmän här. Speciellt när det är stora mässor och konferenser i stan. Men familjefäderna, de kommer hit på helgerna, sent. Eller på måndagmorgnarna när de är trötta efter helgen med familjen. Ingen av dem vill prata, för de går hit i hemlighet. Så om man vill veta någonting om männen här, så måste man tala med kvinnorna.
Can you tell us about the men you meet here?
It's okay. This job don't make me feel think bad about the people or about the men, you know. The men are men, you know. Have to.
No, tell me what's.
No, I think the men have to, I would say, to escape a little bit, you know.
No, why?
Why?
What are they escaping from?
If I have a boyfriend or I prefer to go to a woman to pay and after come home than to go outside with one girl and every day and go to a restaurant, go to the cinema, go to the hotel, and every time the same girls. That make me think it's something, it's a feeling, you know. Mm-hmm. But when the men come and pay a woman, it's everything cold. It's like escape, just a few seconds and you go. And maybe he don't see this girl never, you know.
What's the hardest thing about this work?
The beginning is very hard because you don't have used to the people, everybody touching you, you know, and it's very hard for the psychic, you know, you have to control yourself, and you have to thinking you do only for the money because you need it, or maybe you have some problem, you have to make it, you know, and that's why, you know. But after you get used and you keep going.
With my girlfriend, we stayed at our parents' house for 1 week. 1 week without sex, because the parents are, they don't want, and my girlfriend doesn't want to have sex at her home.